Good afternoon, everyone. I hope everyone's enjoying their pizza. My name is Tyler, and my teammates are Paul, John, Gunnar, Zach, and Josiah. Today we'll be talking about our project, the Quincy Mine Tram. For those of you who are unfamiliar, the Quincy Mine Tram is a critical part of Hancock's very own Quincy Mine Tour and helps deliver tour attendees from the top of the hill near the Quincy Mine to the mine entrance, a 5 to 7 minute trip moving at a brisk 2 miles per hour. The tram sits on top of a set of rails with a third center rail, which allows the tram to drive itself via a very long rack and pinion system. Currently, the inside of the tram is very loud and prevents tour guides from talking to their guests, greatly reducing the interaction time and causing great discomfort to the visitors. On the trip up the hill, the tram driver sits in the rear driver's compartment and suffers extremely loud working conditions capable of causing extreme discomfort during the short 5-minute trip, which has warranted the use of hearing protection. To start things off, I'll give you a short tour of the tram. The front of the tram houses the passenger compartment where the tour guide is able to interact with the tour's attendees. On the way down the hill, it is in the passenger compartment where the driver sits. Directly behind the passenger compartment is the hydraulic compartment, which houses the hydraulic compressor critical for running the tram's brake systems. In the rear right corner of the tram is where the driver sits on their way back up the hill. And directly flanking the driver's compartment is the 6-cylinder, 255 horsepower engine which drives the tram.
Here's a clip of what the tram sounds like inside the passenger compartment. When evaluating the acoustic characteristics of the tram, our team had to keep track of 4 compartments: the passenger compartment, the accumulator room, the engine compartment, and the driver compartment. The shown heat map plot shows the sound pressure level in each one of the compartments, white being the highest sound pressure level and blue being the lowest. Additionally, we took outside measurements for reference.
The largest sound pressure source is coming from the diesel engine powering the tram. Looking at the engine compartment, the team began investigating the available space to attenuate the 113.7 decibel sound level projected from the engine cavity. The next step was to investigate the available space for sound attenuation within the hydraulic compartment. The hydraulic compartment is housed between the engine and passenger compartment and provides a very little transmission loss in the current configuration. The last step of attenuating the sound path through the tram was to look at the available options within the passenger compartment. This is very important to allow the tour guide to effectively communicate to the guests during operation.
Next, we used MATLAB to read through all of the SLM data files and then generate third octave plots for each recording location. The 4 shown here are in the front and rear cabin or passenger compartment, as well as inside the engine and driver compartments. Equivalent sound pressure levels, A-weighted, in the engine compartment itself can be in excess of 113 dBA, but in the driver compartment itself, they can get up to 93 dBA, which is very loud for a driver who works in the tram all day. We can also see from this data that if we look at the revved rear cabin plot, that the sound pressure levels peak at around 250 Hz, which also corresponds with the firing order of the engine, and this tells us that the engine is one of the most prominent sources.
The team has proposed 4 potential locations for adding lizard skin sound control material on either side of the partition between the engine and hydraulic compartments and either side of the partition between the hydraulic and passenger compartments. Material could also be added to both these locations to maximize the transmission loss, but will be more expensive. For the driver, we propose proper hearing protection be worn to reduce the risk of hearing damage. This octave plot shows the effects of different treatment options. Adding 4 layers of lizard skin material to the wall between the accumulator room and engine compartment and between the accumulator room and passenger compartments have the same effect on noise levels and a 3.3 dBA noise reduction. Adding material between the accumulator and engine compartment is a much cheaper option because it requires a smaller surface area to cover. Adding 4 layers to both partitions will have the greatest effect and a significant noise reduction of 6.7 dBA and will cost about $510.
Shown here are some comparisons of the effects of noise on people, before and after treatment. The driver's noise dose was 0.26 and 1.24 by OSHA and NIOSH standards, respectively. After treatment, these numbers are lower, and the driver needs only at least 1 decibel insertion loss hearing protection to put them below the NIOSH limit. Before treatment, the subjective loudness was between 43 and 49 zones, being roughly 12% louder in the back of the tram. After treatment, the subjective loudness was between 24 and 28 zones, roughly a 45% reduction. Before treatment, the speech intelligibility level was 5.4, giving a poor speech intelligibility. After treatment, speech intelligibility increased to fair at a level of 12. To simulate an attenuation of the exhaust noise, the team attempted to create an overkill muffler setup that would reduce the exhaust sound level. The team had hoped to use this observed reduction to understand the benefit of an improved muffler design. Unfortunately, the team was not able to gather valuable data from this overkill experiment, as it was not properly sized for the engine and test. The team did, however, observe a 3 decibel decrease in SPL at idle conditions.
When looking at a source, path, and receiver, we spent most of our time looking at the path. Unfortunately, linking is a big problem for vehicles, as there are many paths for sounds to travel. Although there are many solutions as well, including replacing the muffler and noise dampening flooring.